Okay, let's start. 1, 2, 3, 4. Let's start recording. Fine. The Zoom is still unhappy. One, two, hard. Watch time. One, hard. Hard. Okay. Jay, can you hear me? You're the one on Zoom. Jake, you're the one on Zoom. Can you hear me? I guess cannot hear me. In microphone. Hard. Hope it will be fine. If you cannot hear me, okay, fine. And can you hear me now? So switch the microphone. Thanks. Great. Let's start. I try to bring more cameras. Meantime, we covered yesterday the big O, big omega, and big theta. Any questions about it? Plenty of examples that are coming about it, about when do we say that something is big omega, when do we say that something is big big O, bounding from above, much more common. Our algorithm is not too slow. Big omega bounding from below, our algorithm is at least as slow as, for example, in sorting, it will be n log n. That would be one common claim that is not exactly accurate, but so I'll add it with quarters that, roughly speaking, sorting n keys takes omega of n log n, quote, which means that under some not too ridiculous assumption, pretty realistic assumption, if you want to sort n keys, you'll need any algorithm in the world will take n log n, which, to phrase it even in a more confusing and obnoxious way, it will mean that for each algorithm, for each sorting algorithm, there is an input that cause this alg to run in at least omega n log n, no less than omega n log n. And I bet that it will be a good investment if in the future if I will bring some markets for my room because it's one of them.
Is he saying that all sorting algorithms are at least analogous? Yeah.
Especially for the videos, this semi-white, semi-blue color, not very good. Okay, so this is a bit more obnoxious and a bit more detailed than we most cases will use, but it wants to say I can create a sorting algorithm that would be extremely fast sometimes. For example, I look at the input array and check if this array is already sorted, and then I have to do very little linear time. I can figure it out. However, no matter what algorithm it is, I can generate an input that for your particular algorithm. Once I'm very well familiar with your algorithm, I'll be able to generate at least one input that is bad for you. But maybe it's excellent for other algorithms. So that would be one case that we'll use lower bound. Another very common case, which again I'll write here with even more quotes because it's not really true, but to solving the TSP with n cities takes omega of 2 to the n. It's even more quotes because, again, it's not very accurate, but it gives you a good spirit of what's going on. TSP is a traveling salesperson problem, which is essentially saying I'm giving you a map or a graph of cities. That would be city 5, city 1, and so on. I'll tell you that the length of this road is 200 miles, the length of this road is 200 miles, and so on for each one of the roads. And TSP, traveling salesperson problem, is find a path maybe it is this path, maybe it's a different path, which is as short as possible and visits all the cities. It is as short as possible and visits all the cities. And this problem is one of the famous NP-hard problems. And unless P equal NP, most people believe that it requires at least exponential running time, omega running time. Again, sometimes you can solve TSP accurately much faster, sometimes. But it doesn't mean that for every input you can generate such a case. Okay, and from time to time I'll take a look at the chat of the Zoom. For real estate on my screen, I cannot look at both the chat of the Zoom and the chat of Twitch. So I'm just looking at the chat of the Zoom from time to time to see if there are any questions. So Jake et al., if you have anything to ask, please do. Okay, and then we were talking about the theta notation that says I already gave n algorithm that solves the problem in, say, n log n. Sorting, maybe I can do in order of n log n. We'll talk about a few algorithms that actually provide n log n running time. And if there is an omega n log n lower bound, you cannot do it better than n log n, then your algorithm runs in optimal time. Right? It's no less than n log n, no more than omega of n log n. That's where we were yesterday. Questions so far? Okay, we went through this slide. Let's play with some examples. I generate this function in no specific language, pseudo code, which is one of the questions that I'm facing every time that I'm teaching the course. What is exactly legit pseudocode? And there is no good answer to it. There is no, I'll say it's a code that any programmer, no matter whom or where, any programmer can take the pseudocode and make it into a real code that runs in real computer language without understanding anything about your algorithm. You can translate each language, each sentence that you wrote into a piece of code that is clearly understood. No doubts of understanding how to make it real. So here I wrote in, because I'll ask you sometimes in homeworks to write, your algorithms are pseudocodes. So it's a question that we will face many times. The function no need, method function, a recursive function, and no need takes as an input a number n, and if n is smaller than 1, then it returns, meaning it doesn't do anything, it just returns as it. Don't call it, don't continue to the next line. Otherwise, if n is anywhere larger than a1, then I print an asterisk, and I code no need recursively with no need, but the parameter that I give it right now is n minus 1. And my question for you is what is the running time of this function as a function of n? So for the double use of the word function in two different contexts. So this method, what's its running time as a function of n? It's not a hard question in any way, and there is various different methods to solve it, but it's also our first opportunity to see recursive formulas. Now, recursion formulas, they are important. Recursive formula are important. To my taste, they are important in the same way that going to the dentist is important. It's like, sure, we will have to touch or to go through it. I'm not expect you to enjoy it more than I enjoy it. And I'm not going to make this course into let's solve each and every recursion formula out there, or even giving you a very general tool. So I'm going to show you a few cases that are very common, that appears a lot even in this course, give you a bit of understanding what's going on in recursion formulas, and move on. Okay. If you are math majors, some of the discussion about recursion formula will look similar to differential equations, but and some of the methods are similar. But if you don't know anything about it, that's fine. So just to understand what this function is doing, if I'll call this function with a parameter 4, t of 4, n equal 4, then what this function will do is evaluate is 4 smaller than 1, know that otherwise we are printing 1 asterisk, calling ourselves recursively with t of n minus 1, no need with n minus 1, which will print yet another asterisk, called ourselves with n minus 1 the current n, making it 2, adding one more star to the 2 stars that I already had. It's the same, no, that's a bit confusing. It's the same 2 star and yet printing one more star. Calling myself with a value 1, print a star because 1 is not smaller than 1, print yet another star t of 1, calling myself with 0, and in this case I perform the return. How much time does the whole process take? Obviously, it's only takes a constant time per each iteration, so it's order n. And I want to introduce you to a few methods to go to the answer that it's order n. You can reach to it in a few ways. You can use, maybe you've seen in other courses, you can use a master theorem. Master theorems is a very general tool that you are deciding what the general look of your recursion formula and placing it in, and you're getting the answer of what the running time is, what this function solves. And maybe before that I did not really tell you what am I evaluate by, what is t of n right here. I actually skipped an option. When I'm asking what is t of n, I want to know t here for time. T for time would be the running time on the running time as a function of n. And I skip it. Usually n is the size of our input. There is some array or some file that is going on with it that contains n parameters, but since this is, I wanted it to be a very clean abstract exercise, n is just an number. And to express any recursion formula, I need to express this formula. In this case, it has only one parameter, t of n, as a function of values which are depends either constants or depending on n, but smaller values of n. So instead of, it's the cases that it's much easier to understand what am I saying by just examples. So in our case, if t of n is running time for a value of n, then t of 1, if I called my function but n equal 1, then this function will spend some constant time. I can call it 1, I can call it c, doesn't matter. Some constant, again, I don't care what is this constant, depending how fast my compiler works. depending how I measure the time. But once I decided about what is this constant, I cannot change my mind. This constant cannot be depending in any way in n. Otherwise, for any other value of n, especially if n is larger than 1, then T of n consists of what? I'm spending a constant, and for simplicity, I'll use the same constant. Maybe it's not this C and this C are not exactly the same constant, then I'll use the larger of the two. Why? Where is this constant coming from? Because you evaluate here what is the value of n. You are putting things in the stack of the recursion. You know, you need to print these asterisks. You need to put more things in the function. And then you're calling yourself this function recursively, but with a smaller n, maybe smaller, just part of the input, which we can write as T of n minus 1. And that will be a general look of recursion formulas, where what is T of n or something smaller than n, and sometimes there will be some other constants involved. And once again, instead of telling you very accurate rules, we are just going to see a few examples of recursion formulas, and you will all be experts. Trust me about it. So how do I solve recursion formula? I want to know, what do I mean by solving the recursion formula? I want to know what is T of n, in this case, the running time of input of n, but not as an obscure expression of T of other values right here. I want to know, is this order n? Is this order n squared? Is this 2 to the n? Give me a concrete number. And one method, that's what I mean by solving the recursion formula. When you see it in the homework, solving the recursion formula, understand you want to write T of n equal, and in the right hand of the expression, there should be some T of n equals and something here where T does not appear on the right hand side. One way to solve it is the master theorem. It's a big artillery tool. It solves many problems. It gives you very little intuition about what's going on. And I don't think that you study anything from using it. So, but if you are used to use it and want to solve your homework using the master theorem, unless I'm asking specifically, don't use it, I will accept it. It's still a correct answer. In this deliberately very, very simple example, I want to show you a different method called the iterative method. Let's try to understand what this function looks like when we are going through the iterations. Let's try to understand what the behavior of this function, what is the behavior of this code. So what is T of n? And remember, T here is a running time. The running time of, say, input of size n. It consists of what? It consists of a constant, no matter what. You always have to waste this constant, plus call yourself on this function, T of n minus 1, recursively. That's the point where I'm a bit afraid that if you didn't see many cases of recursion earlier, you might not be crazy about this. This might look very vague. So Q of n is just a constant plus running time on, maybe the input after you removed one element. The array is not of size n, but of size n minus 1. That's the array. Great, what is therefore T of n minus 1? I want to show that I made any progress. Q of n minus 1, calling this function, but we instead of n use n minus 1, is what? You're spending the same constant, no matter what, plus T of, it was n minus 1, making it n minus 2. So what do we have so far? C that came from the original, plus C plus T of n minus 2, just rearranging it, 2c plus T of n minus 2. Fantastic. What is T of n minus 2? Let's do one more step. T of n minus 2 is just the same constant, c plus T of n minus 2 minus 1, making it n minus 3. And you already have from earlier this 2c that comes right here. So we are getting to 3c plus T of n minus 3. And at this point, we can guesstimate what happened after k step, where k is any value between 1 and n. What will it look like after k step? So k is any number. Well, we take k equal 4, 5, 6, all the way up to n. What are we getting? We will collect k times c, no matter what k is, as long as it's smaller than n, plus T of, instead of the 3, I just write it k over here. Okay, so for any value of k which is between smaller than n, the running time will be kc plus, still calling myself recursively, but at least I'm closer to the end of this process. T of n minus k, and this is true for every k. In particular, it's true if I take k, which is n minus 1. So what did I get altogether? K is n minus 1, so it's n minus 1 times c, plus T of n minus 1, making it T of 1. T of 1 is a constant, but T of 1 will just call itself once again, so it's 2c if you want instead of c, but we don't care. So altogether, we are spending n times c, which is order n. Everybody agrees? So n times c is just order n. That's the beauty about using the order. Did I make a mistake and I should have written here n plus 1 instead of n? Who cares? This is type of mistakes that a big O is immune against. It doesn't pay attention to if it's n or n minus 1 or n divided by 2. Still order n times a constant, making it linear time. Not surprising, just seeing how we are using this recursive formula. Next example. And I like this example because it will demonstrate a few tools that we are going to reuse multiple times in the course. Again, I called it no need. Again, if n is smaller than 1, then do absolutely nothing, just return. That is, you might call yourself recursively, but the last call, just return and do absolutely nothing. Otherwise, I'll do something and then I'll call myself recursively with n minus 1. That's exactly what we saw in the previous slide. Do something and call yourself recursively with value of n, not n, but n minus 1. But earlier in the previous slide, this line was print 1 asterisk. In this example, I'm printing a lot of asterisks. Actually, I'm printing from I equal 1 until I equal n. I'm printing n, maybe n minus 1, many asterisks. And once again, I want to know what is T of n, what is the running time for a value of n that you're using right here. So first, let's write what is a recursive formula. Recursion formula.
Professor,
Alone.
you know, this slide and the previous one is not on the PDF.
It's not on the PDF right now?
In the syllabus.
Did you check right now? If you,
Yeah.
or since yesterday, I think that I uploaded it.
I can check right now.
Okay. I mean, Yeah. It is?
Yeah, it is not.
Okay, I'll add it later. So that. Okay, then I'll just use, I'll be more accurate on the whiteboard. And let's see that the OBS gets me more or less right. Yeah. Okay, so first, what is a recursive formula? T of 1 equals, just like before, a constant. Maybe it's different constant, still a constant. Earlier, so good time. Introduce yourself. Yeah.
Hello everyone, I'm Amir, I'm the TA. I will have office hours on Tuesdays. I can't remember the next day. And Thursdays, professor has Monday and Friday. You're welcome to come to my office hours and ask your questions.
And I personally very happy to work with Amir. It's like the second course and also TA student, but tell a bit about your background. It's quite impressive.
Well, I was an SIE student initially, but then I changed to computer science. I did a lot of programming and stuff. I love game engines, making games and stuff. Right now I'm working on geospatial things like GIS and a little bit machine learning graphical models. So yeah.
And your degrees?
I had undergrad in SI in industrial engineering, then masters in industrial engineering, then another masters in systems engineering. Now I'm a PhD in computer science. Thank you.
We can go on, and we are solving COVID in sort of.
Are they Zoom only or
Uh,
online or in person only?
So far it's only on Zoom. Professor, if you want, I can put one in person.
If you'll ask, we'll be here, definitely. The day of the courses, definitely. We'll be here as well.
If you want, you can like put on Piazza and ask Professor. I should ask Crystal to set a place for in person. So far it's just online.
And quick question, can you go on Zoom to me and just see that, let me know if there are questions on the Zoom. Okay. T of 1 equals a 1, obviously. Let's decide later if it no helps one camera and it destroys the other one, so it's not. Try to white larger. Now, T of n was earlier. What we saw was in the previous example, it was T1, C plus T of n minus 1. That was in the previous example. Now I'm still using T of n for any n larger than 1. It is not 1C, but I need to accumulate for all the asterisks that I print over here. So it is C O times N. C times N, maybe it's N minus 1, but again, that's a type of noise that the recursion formula doesn't care about. Plus, once again, T of N minus 1. That's the difference is instead of C plus this creature, it's C times N plus this creature. And once again, I want to use the iterative method to express what's going on here. So let's go through the iteration. T of n is, that I just wrote on the whiteboard, it's T of n plus T of n minus 1. Once again, if you lost me, the running time of the input of size n is the constant times n, plus call yourself recursively with slightly smaller input of size n minus 1. What does this equal to? Let's use the iterative method. Well, it's just a C of n that I copied from here. What is T of n minus 1? It is just, let's put n minus 1 over here. It's C times n minus 1 plus T of n minus 2. Rearrange it. It's C times n plus n minus 1 plus, and now what is T of n minus 2? It is just C times n minus 2 plus T of n minus 3. Let's rearrange it. It is C times n plus n minus 1 plus n minus 2 plus n minus 3 plus T of n minus 4. I jumped one step ahead. Okay, at this, remember from the n came from here, the n minus 1 came from here, the n minus 2 came from here, and so on, just accumulating more and more stars. Notice that if you call this function recursively, the number of stars will look like you have 4, and then the next call you'll have 3, the next call you'll have 2, the next call you'll have 1, and then 0. Then you'll get a return. That kind of gives you a hint where things are heading toward. At this point, with all these ugly creatures floating around, I can guesstimate what happens if I take any value of k between 1 and n, arbitrary k. What's happening with this? I'll collect C times n, n minus 1, n minus 2, n minus all the way up to n minus k, plus T of n minus k minus 1. N minus k minus 1. This is true for every k. In particular, it's true for k, which is n minus 1, which happens to be, now it looks ugly, T of 1 over here that will give me the constant. Now there is this summation over here, which looks very confusing looking from left to right, so instead I'll read it from right to left. What's written here from right to left? It is 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n. Switching the order, let's take this summation in the square brackets. Reverse the order, it is 1 plus 2 plus 3 plus 4 plus all the way up to n, which will appear many times in the course. This is just the arithmetic sum. Hopefully you all know it. It is 1 plus 2 plus all the way up to n. It has a formula that tells you exactly what it is. It is n times n plus 1 divided by 2. Supposedly Euler found it when he was 9, when he had to sum up 100 numbers in class. So he just realized that if I look at a square of size n times n, this square has n star, n square many stars, and what I have in this sum is just one triangle, half of this sum. So you see that this number is more or less n square half, the full half of the square. Make sense? Or another way to think about it is if you're summing up 1 plus 2 plus 3 plus 4, I want to ask how many squares there are over here. I'll take this square. Actually, I want to have one more. So actually it's fine. I'll take this square and move it to be right here. I'll take this square and move both of them to be right here if I'll have more squares over here. I'll keep doing it, but altogether you're getting a set of rectangles. Each one of them takes the first and the last, one from the first and one from the last, and so on, and you're getting height of n plus 1, that's the height of each of these rectangles. And how many rectangles do you have? I started with n rectangles. Each time that I moved one of these rectangles, I decrease the number by 1. I merge 2 into 1, so I roughly have n half many rectangles times n plus 1, and that's the exact calculation. Okay, back to our. So make sure that you feel familiar with this formula. And altogether, the running time is therefore order of n squared, which is also omega of n squared. But that's exact number. There is no ifs and maybe here. There is no friendly and unfriendly input. So it's not less than n squared. It's not more than n squared. It's order of n squared and omega of n squared, making it theta of n squared. Tight bar. Questions? Again, make sure you are familiar with this example. Yeah.
In like homework and stuff, if we just put O of n squared, would that be okay?
Depending on the question. I'll usually ask if I want both upper and lower bound, then no. As a default, usually yes. If I don't write anything, just analyze the running time, you'll just get away with the order. Maybe. Okay, here is another function, not recursively in this case. Read n, k is 1, and as long as k is smaller than n, do k equals 2 times k. Okay. Here I will need to use logs quite frequently. I'll remind you, I don't know, when and if you were in high school, reminded what is log. So in general, if I look at log to the base 2 of say 8, my question here is write 2 and write something here in this box, exponent of the 2, so the result will be 8. But that's what the question that logs tries to answer. If you look at the base of the log and write some exponent, take this base and do it to the power of something, what should be the something, so the result will be the argument of the log. So the answer in this case is, of course, 3, because 2 to the power 3 equals 8. We what are the common base to work with log? Log to the base e, lan, very common. Log to the base 2 because we are in computer science. Log to the base 10 because we are humans. That would be the common ones. Here are a few rules that works no matter what the base is. If I have two numbers, a and b, and I look at log, no matter what the base, of a times b, it's just like take the log of a and add to it the log of b. Of course, the base of the log, this small number over here, should be the same in all when you're using the logs in all three places. Okay, log of a times b is log of a plus log of b. That's my favorite, log of a to the power of b. You always see exponent of the argument of the log. You're picking the exponent and write it before the log. Take the exponent. Log of 2 to the k is just k log of 2. No matter what I actually write for any value. Just take the exponent and write it before the log. This formula tells you to move from one base of the log to the other. You want to write log to the base 2 and log to the base 10, say. So logs to the base a of x equals logs to the other base of x times some constant. Yeah, you can compute this constant log to the base b of a, as we'll see. We'll rarely care about what is this constant. We will care that moving from one base to another is just multiplying or dividing by a constant. One more rule, if x is smaller than y, and both positive, by the way, should say, both positive, x is smaller than y, then log, no matter what the base, if it's larger than 1, log to the base 2 of x is smaller than log to the base 2 of y. Okay, now we are ready to analyze this code. I can write recursive formula, but let's skip it because it's simple enough. I want to know, I'm looking at this number k, and I want to consider the evolution of k as we are going through the while loop. What happened to it every time that we evaluate the while loop, and the while says, yes, this condition is still holds. Let's see what happens to k at this value. What happens in my first iteration, the first time that I evaluate this while, k equals to, when I'm evaluating it, when I'm after evaluating it in the first time, k will be 2 times, it used to be 1, now it's 2, so k is 2. After one pass through this loop. Another pass through this loop, k is still smaller than n, k equals 2 times k, so k equals 2 times 2, which we can prove is 4. Another iteration, after the third iteration, k is 8, which I'll methodically insist that I'll write this 8 as 2 to the power 3 for a reason. What happens after another iteration? We start the other iteration when k equals 2 to the I, to some value I, and now I'm performing k equals 2k, implying k, the new one, equals 2 times 2 to the I, which I can also write as 2 to the I plus 1. Just looking for chat, everybody's happy. Okay, so Makes sense, right? So that is after I iteration, k is just 2 to the I. After the first iteration, k, after iteration 1, k is 2 to the power 1. After iteration 2, k is 2 to the 2. 2 to the 3, after I iteration, it's 2 to the I. And we're almost done. Let's ask how many times do I get the answer yes to this condition? I'll measure the time, but to measure the time, let's ask how many times are we getting the answer true, this condition still holds. How many times can it happen as a function of n? Because overall time, running time would be all the times that you're getting the answer yes, plus 1 time that you're getting the answer no. So let's just ask how many times we are getting the answer yes. So if we are getting the answer yes, it is because the current value of k, what is the current value of k after I iteration? It is, after j iteration, k is 2 to the j. That's what I just said. After j iteration, switch to I, from I to j, after j iteration, k is just 2 to the j. J equal 1, 2, 3, and so on. And I said that I'm counting only cases at which the answer to this condition was still positive. That is, this new k is still smaller or equal than n. 2 to the j is smaller or equal than n. How large can j be? You already guessed what the answer, but let's do it a bit slowly because the first time. How large can j be? And this condition can still hold. Let's see it methodologically. If doesn't need much explanation, but if x is smaller than y, if x is smaller or equal than y, then log, no matter what the base of x, is smaller or equal than log, no matter what the base of y. Exactly what I wrote here. If and only if. That's because log is just monotonically increasing. So if 2 to the j is smaller than n, then if I take log of this, it will be smaller than log of this. If this is smaller than this, then log of this will be smaller than log of this. What is log of this, the left side? Log to the base 2 of the current value of k. What is k right now? It's 2 to the power j. Log of k is log of 2 to the power j. It's written actually better here. Log of k is log of 2 to the power j. What do I do every time that I see an exponent inside the log? I take the j and I write it before the log. So this is j times log to the base 2 of 2. It's the first time that we see it, so let's do it a bit slowly. What's the question of log trying to ask? I'm asking log to the base 2 of 2. Try to answer. If I write 2 to the power of something, what will I do so that I'll get the number 2? What should be the exponent right here? Let's think about it really hard. My hint, it's 1. Log to the base 2 of 2 is just 1, because 2 to the power 1 is 2. I think that the more I talk about it, the less obvious it becomes. So it's j times log to the base 2 of 2, which is what we just said. This creature is, this is just 1. That's why I wrote it over here. So I'm just left with j. J, remember, some arbitrary iterations for which I still got the answer yes in the while over here. So j, and what did I write on the right hand side over here? All this expression that happened on the left side is still smaller or equal than log of what's written here, which is log to the base 2 of n. So j is smaller or equal than log to the base 2 of n. That is the j number of iterations that you can do which are still positive is order of log to the base 2 of n. You cannot do more than log to the base 2 of n. All iterations are successful. The answer is yes. You will do one where the answer is no, but only one where you stop. So J is order of log to the base 2 of n. And then you are asking, hey, didn't you say that when you're writing the big O, you don't care what's a constant out there inside the big O? We don't care. If you multiply the constant from years to weeks, big O should still remember. So here we write log to the base 2 of n, log to the base 2 of n. What happens if I want to express it as log to the base 10 of n? I need to take the log to the base 2 of n and multiply or divide by this log a of b. It's a constant. So if I'm writing log to the base 2 of n, I might as well write log to the base 10 or log to the base e, or not write the base at all, because it's inside the big O. Conclusion, every time that you say big O, you don't care about the base of the log. Okay. Now, how should we do it? The three of you, the two of you, and the people at the Zoom, and also the guys, we will do some questions from time to time. A non-trivial question, but let's challenge you. So the three of you can discuss, and the two of you can discuss. I read n k equals, let's start this time with 2, and while k is smaller or equals than n, do k equal k times k squared. So instead of 2 times k, I'll write k times k. Take 2 to 3 minutes, it's not easy, but what is the running time of this creature? And so to view, and 3 people in the Zoom, because it's 3 people, then I will not open a room for you. For the future, I'll open a room so you can, by the way, and the hint to start is, start by writing what is the value of k after each iteration. Write what is the value of k after each iteration. You'll need a few more iterations before you fill it. For the people in Zoom, I have some of you are yeah, it's so yeah. And the hint is that for the first iteration, of course, k is equal to, not surprising, the next k will be 4, but that's a bit confusing, misleading actually. So I'll write it as 2 to the 2. This iteration already should give you a hint. What happened after the third iteration when k is 2 to the 2, the 4 that we had earlier, times, it's not 2, but to the power of 2 to the 2. From here you should start to get an intuition. But that's not an exam question, it's much harder. The next iteration, it will be k equal to 2 to the 2. I'll write it larger. Next iteration, k equals 2 to the 2 times 2 to the 2. And let's use another piece of algebra, arithmetic that you know hopefully from somewhere. 2 to the power of a times 2 to the power of b equals
2 to the power of a plus b.
equals 2 to the power a plus b. So as usual, we are trying to ask what happened after I iterations. I equal 1, 2, 3, 4. So this expression, 2 to the 2 times 2 to the 2 equals equals 2 to the 4. Let's move another iteration. What happened to the next k? It will be 2 to the 4 times 2 to the 4. Okay, and in the next iteration it will be 2 to the 8, 2 to the 8 plus 8, making it 16. So after I iterations, k equals 2 to the power of 2i. That's absolutely correct. And that's why the overall running time will be, if we are doing something similar to this, I want to get that k or that I, okay, over here, is smaller than some function of n. How can I get I smaller than something? Well, I want to say this while still going on, so this number is smaller than n. 2 to the power of 2i is still smaller than n. 2 to the 2 to the I is smaller than n. So I is small or equal than, help? Log n we had in the previous case. Let's try. Let's take log from both cases. Then we are getting, let's take log from both cases. both sides. So I'm getting from the left log to the base 2. All my logs are in base 2, or it just these many forms. Log of 2 to the 2 to the I should be smaller than log n. So far, so good. Smaller than log n, but this number is not I times 1, as we have right here. I still take the exponent and write it before, so I'm getting that this number is, let's take the exponent, 2 to the I times log of 1 is smaller than log n. Then log of 2, thanks. Log of 2. 2 to the I times log 2 is smaller than log n. So I is smaller than you're older. I is smaller than Jake. Two to the I times 1. 2 to the I times 1 is smaller or equal than log n, but I want to get I is the iteration number.
Is it is it 2 to the I less than?
2 to the I is smaller than log n.
Is it log
Log n, very nice. Let's do log this, exactly the same exercise, the same gymnastics that we did from here to here. Let's do it one more time. Take log of both sides. So I is smaller or equal than log of n. Okay. So very nice, good job. And and surprisingly, there is many algorithms that have similar performances. You can definitely beat the log n performances in many cases. Questions? Okay, more examples coming over. Back to this example. Before we are leaving this one, I want to have another one relative of this one. With n, k equals n, and while k is larger than 1, do k equal k divided by 2 and take the ceiling. It's a relative of this guy. What's the running time? So to start with, let's assume that n is is a nice number. N equal 2 to the I for integer I. Then I don't need the ceiling because when I divide it by 2, it's still an integer number. So how many times, I start with some number n, how many times can I divide it by 2 until I'm getting 1? Log to the base 2 of n. Here I started from k equal 1 and multiply it by 2. Here I start from n and divide it by 2, but it's exactly the same operation, the mirror operation. Okay, I can also write the same code just in a recursive way. No need of n. If n is larger than 1, then return. Else print star and no need of n divided by 2. It's the same thing, just recursive. N that's called n over half, or half called n over 4, called over 8. Why do I print the star here? Is just so you'll feel that something happens in each part. I'm asking. The running time is just proportional to how many stars, how many asterisks I print. Okay. Want to look at this code. It's a bit similar to some sorting algorithm. And I want to ask what is its running time. That's actually a pretty tricky question. So read n for I goes from 1 to n, I plus plus. And here goes another loop inside it for j start from I. J is smaller than n, j. But here's something strange happens. Let's start when I replace this line by j equal, instead of j equals j plus I, which is, that's just a shorthand to j equal j plus I. Let's start by what is the running time when I write j equal j plus 1. So after this modification that I suggested, how many asterisks do I print? I'm calling the outer loop n times. The outer loop called the inner loop with a new modification n times. So the number of asterisks that I print is exactly n squared, which is order of n squared and omega of n squared and theta of n squared. But now let's undo this change. So now I'm adding to j I at each iteration. And things here are actually quite surprising. So first, you notice that when I equal 1, then the inner loop is called the same number of times. I'm just adding to j I, which is 1 at each iteration. So I'm doing it n times in the first iteration. But the next iteration, when I is 2, then I'm not calling it so many times. I'm just going through some subset of the elements. And then I'm increasing I even more, so I'm only going through some subset of the elements. So that's start to be a bit more confusing. Jake, do you have an answer for this slide that I'm flashing at the moment? Log n is not the answer, but I think that your sense of smell is correct. So it's not omega of n squared. I want to say if I would use it before the change, then it's omega of n squared, order n squared, theta n squared, its type. But here I want to claim that it's still true to say that even with, restart. Question mark. Is this order of n squared? Yes or no? The running time of this algorithm. I'll ask each one of you. Order of n squared, yes or no? You said no. You have to remember exactly my wording from yesterday. You say?
Yes.
You said that it's order of n squared. I mean, with a new modification. The code, sorry, I didn't say it clearly. With a modification, that is, I'm doing the modification, this code, as it appears on the slide. Is this order of n squared, yes or no? You say
Yes.
yes. You say no. And the answer is that it is yes, but it is yes in some very cheatful, dishonest way. It is not more than n squared because this new modification somehow saves some work. But what did I say that my lawyer said about order n? It doesn't take more than n squared. The outer loop doesn't happen more than n times. The inner loop will take either n or something smaller than n, but not more than n. So order of n times order of n is still order of n squared. So in a cheatful way, it is still order of n squared even after the modification. But maybe it's better, maybe it's constant. Constant is also order of n squared, which is why I'm asking, is this also true that it's omega of n squared?
So on the homework, I mean, like, to have a correct answer for the O notation, I mean, we would always be correct if we say, oh, you know, something is O of n cubed or O of n.
That sometimes I'll ask you, well, give a bound that is as tight as possible, or at least up to big O as tight as possible, or give a matching bounds.
It doesn't say
But yes,
that.
I'm well aware of this loophole. Okay, let's try to be a bit more sensitive about what is the running time of this case, just because it's cute and it's surprising. I equal 1 and I execute the inner loop. I equal 1 and I execute the inner loop. What will be the value of j? J starts from I, so j will be 1, then 2, then 3, all the way up to n. So in total, I print n stars. Maybe it's n minus 1. Catch me on this one. I print n stars when I equal 1. Start when I equal j, could have started with I equal 0, all the way up to adding to j 1 at each iteration. Things are a bit more interesting. Let's move to the case I equal 2. How many stars will I add at this case? I start with j equal 2, and the next j that I'll use is j equal 2 plus 2, 4. Next j will be 4 plus 2, 6, 8, 10, and so on. So roughly how many stars do I print? N half. Now, I should have written here ceiling or floor or something, but here is a rule for all the big O notations that we are using. If you have something and you see something that depends on only ceiling or floor, ignore it. I should have actually said it when we talked about the log earlier. Every time that you are dividing something, even if it's not nice integer when you divide it by 2, log will still be the correct. There is a justification for it in the book. We rarely care about floor and ceiling in this course. If I divide an array into 2 halves, then as far as I care, each half is of size n half. Even though one is n half plus 1 and one is n half minus 1, don't worry about it. It doesn't really affect the running time. So I'll say when I equal 1, I'm printing n half many stars. Plus minus 1, just this. Let's go to I equal 3. What will be j? Start from 3, jump to 6, jump to 9, jump to 12. All the numbers which are divided by 3. How many numbers that are divided by 3 can you find between 1 and n? Well, n over 3, plus minus 1. But every third number is participated here in the j. Okay, one more, I equal 4, then j will jump to 4, 8, 12, 16. How many numbers that are divided by 4? Every fourth number is picked, so n over 4. Dot, 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 dot. Now I finally, my last loop, I equals n, so I equal n, so I print n over n, only 1 star, asterisk. How many stars did I print altogether? N plus n half plus n over 3 plus n over all 4 plus dot, 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 which are missing here, all the way up to n divided by n. So the running time is n plus n half plus n over 3 plus n over 4 plus dot 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 n divided by n, which I can write as all these elements have n in them. So I'll open big parentheses and I'll write n times 1 plus half plus 1 over 3 plus 1 over 4 plus 1 over the last element, 1 over n. That's the last element. Some of you know it, some not necessary. I'll tell you about it when we need it. But this summation of 1 plus half plus 1 over 3 plus all the way up to 1 over n, it has a name. It's called harmonic sum. And it's not accurate, but with very little noise, it's this, what you see here in the summation is ln n. Not entirely obvious, you need a Taylor expansion for it, various calculus tricks, but it equals to ln n. So the overall running time of the algorithm is n ln n, which I think that's the number of stars that you're getting, which implies that it cannot be omega of n squared, of course. It can, because omega of n squared is more than n ln n. Okay, that would be one of the more complicated examples that we'll cover. Okay, here on the other hand is an example that we'll cover enormously many times. That would be the examples that we'll see in the course infinitely many times. Read n, I'll set a to be half, and while n is larger than n, print n stars and multiply n by half. And do the whole thing again, as long as n is larger than n. To meditate on this part for a second, what do? I divide n by half, multiply by a in this case. I divide n by half. Multiply n over 2. And how many stars do I print? First iteration, I print n asterisks. I just write n and I print n with my asterisks. Then I multiply n by half and perform the same loop again. So n is just half of what it used to be originally, and I print n asterisks. I printed n asterisks. Now I print the new n asterisks. How many are there? There are only, the new n is a times n half. But a is half, so I print fewer asterisks, only half of the original number. And then I multiply a by a. Think about it as what happened to n here is that I bought my house when I paid n dollars, and now my house lost 50% of its value. How many dollars do I get? A times n. Now my house lost another 50% of what it already lost 50%. So the new value of n is a times n. A squared times n. It's only 25% of its original value. Another iteration, after k iteration, it would be half times half times half, etc. K times, house doesn't worth much at this point, times n. And I want to ask how many stars did I print altogether? I have one, I'll use 2 minutes on this point. So how many stars did I print altogether? My first iteration, I printed n. One iteration after that, it was not the original n, it was a times n. One iteration after that, it was a times n. Then it was a times a n, and so on. Each iteration, it lost some value until at some point I stop, when my house doesn't worth more than $1. But in I'm going to pay very little attention to when do I stop exactly. You'll see in a second why. Let's write this function again. All these numbers have n in them. So I'll write it as n times 1 plus a, half, plus a squared, quarter, a cube, 1 over 8, 1 over 16, 1 over 34, all the way until I stop at some point. But now what is written right here? At this point, I want you all to remind yourself, what do you know about geometric sums? Geometric sums looks like a to the power of 0, which is 1, plus a squared plus a cube plus all the way up to 80. There is a formula that tells you what this sum, every geometric sum equals to, and this formula is 1 minus a to the power t plus 1 divided by 1 minus a. Too many letters to my taste, much too many letters to my taste. Let's see what does it look like. If a is smaller than 1, then a to the t plus 1 is an extremely small number. A to the t plus 1, if it's half, for example, then a to the t plus 1 is an extremely small number. So let's just ignore it. It's so small, then I might as well add these tiny, tiny minuscule elements all the way to infinity, and then this ugly creature disappears, and you're getting 1 divided by 1 minus a. In our case, a is half, so the 1 minus half, which is 2. So this number, if a is half, then this number is 2. Let's go back to this creature. What do we have here? N times, what is 1 plus half plus quarter plus all the way and continue it even to infinity? What does this equal to? Just say it, 2. From here to here, this summation of 1 plus half plus 1 over 4 plus 1 over 8 plus 1 over 16 dot, dot, dot. Don't confuse with the harmonic sum, because then I had 1 over third, 1 over fourth, 1 over fifth. No, that's geometric. So you have n times all these creatures, which is just n times 1 minus a, which is just 2. So it was very, very easy, if you are following my way, it's very easy to say, oh, the total number of asterisks that you printed here is only 2 times n. It's a bit surprising. My first iteration, I printed n, and overall, altogether, all the iteration after that, I only printed 1 more n, even if I would print minuscule pieces of asterisks. And in all the analysis that I'll ask you to do, you can always assume that you are adding elements all the way to infinity, and then you don't need to calculate when to stop exactly. It's becoming much simpler. And I'll tell you when it's extremely useful, for example, in graphics that we just finished teaching. In graphics, people ask you about, you have a geometric model that is very complicated. And sometimes you want to render it when you're standing next to it, and you need a lot of details. Sometimes it's further away from you, and you need much cruder details. Sometimes it's very far away from you, much cruder details. And the question is, what of all these models should you store? The one with n many triangles, or the one with half many triangles, or the one with only quarter? And the answer is no, store all of them. The one with the n triangles, the one with half many triangles, the one with quarter, well, and you'll ask, but isn't it a lot? And once you need to render it, then you'll decide which of these models do you actually need to use. But memory-wise, you're storing all of them. And you need to ask, wait, but don't you then use tons of extra memory? No, you're using very little extra memory. You're using factor 2 only on the memory. And on the other hand, you have huge advantage about which level of details do you want to use. So make sure that you understand this slide. It's probably the most important one for what we discussed today. Thanks, everybody. See you tomorrow. If I'll have key to the office, how many of you want coffee tomorrow? If no promises, but if. Maybe. 1, maybe. Okay, the black coffee, you know, the one from a